Okay, so let's continue on with the processing now. I'm going to fix the windows on the top controller back. We were looking at the volreg results up there before, so I'll leap back to those and then I'll hit O to turn off the overlay, or I can toggle the button here, whichever. And then I'll jump back to our favorite coordinates from earlier. So jump right click and jump to XYZ, and still 248614 and set. So that's where we had been looking. And now if we continue on with the proc script, we just finished the masking block. Uh, one thing I should mention about blurring is that it's okay to blur after the linear regression as well, except that, for example, when you're running this stuff with AFNI proc.py, it computes the blur estimates from the residuals from the linear regression. So if you blur the data after the linear regression, you should really then blur the residuals and then estimate the blur from those blurred residuals. So a little extra work. For practical purposes, it does not really matter whether you blur before or after the linear regression. The only reason it matters a little bit is because of the scaling block. The applied scaling, the way we do it, can vary slightly across runs. It shouldn't be a big difference, but it's a tiny one, and that makes blurring and regression not quite commutative. But other than that, they would be pretty much. So let's talk about the scaling block. Uh, for each run, we basically want to scale each voxel so that it has a mean of 100. So in order to do that, for each run, we take the current result, which is in this case the blur result, PB03, and then we compute the mean. Then we run 3D Calc with the blur result as dataset A, and the mean as dataset B, and we actually apply the mask, the extents mask here too, because blurring could extend that a bit. And then basically we're taking A over B times 100. That's the basic computation, where you take the regular EPI data, the blurred EPI data, say, divide by the mean and multiply by 100. The effect of that is a constant scaling across time, but so that the new mean will be exactly 100, well, subject to truncation error. And then we just do a little other clipping to make sure we're not dealing with weird values. So if the mean is going to be 100, we don't care about values that are greater than 200. So we clip them so that the maximum, so that we never exceed 200. We take the minimum of 200 and the actual value we care about. And that's just if we're still dealing with signed short data set values, 16-bit integers and signed 16-bit, you only have 15 bits of accuracy. You can only have 32,767 numbers in that, because we're not dealing with negatives at this point. So there's no point in going over 200. I could actually, if I wanted to some degree, there's no reason for not subtracting out the mean here. I kind of like to see the values positive, but it would be quite reasonable to subtract the mean, and then we could restrict this to 100 or even 50. There's no reason to have, these get converted to a percentage of the mean, or you could call it a percent signal change if we subtract the mean. And if we're talking about percent signal change, there's no reason to get too large. So then we could clip it on both the positive and negative ends. But anyway, this is reasonable. We basically have a range from 0 to 100 in here. And then we apply the extents mask, that's dataset C, and we also make sure that neither the mean nor the data are negative for some reason, some strange reason. If that happens, like an interpolation could cause the data to go negative at some point in time, like in the Valreg step. So those are little things, but the basic operation is this. We scale it so that the new mean of each voxel for each run is 100. The fact that we do this independently for runs is why blurring and regression aren't quite commutative. It's close enough. The scaling's not going to vary very much across runs, but it does vary a little bit, so that makes them not so commutative. So let's look at the result of this. So on the bottom we have our blurred input. So let's change the underlay of controller A on top to be run 1 of the scaled result. And lo and behold, we just blew away our data. That's got to be terrible, right? Well, of course, we just scaled it so that the average at each voxel, the average across time, is 100 everywhere. So we've wiped out a lot of the anatomical structure in the EPI data. But if we go to the graph window and click and right-click on the central plot, you see the mean there is 1223. If we do the same up above, the mean is 99.9999. It's effectively 100. We can hop all over the place, even go across slices wherever. The mean is 100.0002. You know, there will be truncation errors in these. So let's jump back. But now compare the shape of the curve, the shape before and after. It's basically identical. There's no difference between the time series shapes before and after on the bottom and on the top. What changed is the scaling of them. Now you can see this is 1187 up to 1288, and this is 97 up to 106. It's just essentially to get from here to the bottom to the top, we're dividing by 12.23 to make the new mean 100 at this voxel. At a different voxel, at this voxel, just the neighbor, we're dividing by 12.34. Okay, so that's the effect of the scaling operation. And why don't I just make a clean break? I'll make this a very short video and then we'll go on to the regression in the next one.